Hello. A very warm good morning, one and all. Welcome to all. Dr. Ajay Soni, resource person, the first session of the third day of this online FDP, and all the participants and my colleagues. First of all, I welcome Dr. Ajay Soni, Associate Professor, IIT Mandi, on behalf of our university. You're welcome, sir. Dr. Ajay Soni is an associate professor at School of Physical Sciences at IIT at Indian Institute of Technology, Mandi, Himachal Pradesh. He has expertise on physics of charge transport, light matter interaction, and structural property correlations in nanomaterials and nano-functional devices. He did his PhD from UGC DAE Consortium for Scientific Research Indore and postdoctoral research from NTU and NUS Singapore. He is recipient of DAE BRNS Young Scientist Research Award 2015 and Best Award from Indo-US Science and Technology Forum 2018 and Research Excellence Award from IIT Mandi at 2021. He has obtained several research grants from various funding agencies. He is an associate editor of journal Material Lab and member of the Young Leaders Editorial Board of Energy and Environmental Materials. So we welcome you, sir. Thank you very much for being with us. So now the session is with you, sir.
So let me share my screen and
yes, sir.
Okay. So is my screen visible?
Yes, sir.
Okay, fantastic. Yeah, thank you very much, Dr. Neetu, for the nice introduction. And at the outset, let me first thank the organizers, Dr. Pragya, and the authorities from the Sri Vaishnav Vidyapith University. It is nice to be talking to the people in Indore because I love the city. Thank you very much for inviting me and giving me a chance to interact with the people who are attending this session. And so what I'm going to talk today is a technology. Let me just put it here. So it's a technology which is known for more than 200 years, and it's evolving with time, and it can provide a solution to the energy demand. So I like the theme of this faculty development program, where the present and future renewable energy sources from lab to the industry. And so I have planned my talk in a way that I'll give you the details about this technology. And then I'll give you the idea that how this technology is evolving with the time. Then I'll give you some examples from the literature and a few of the research work which we have been doing at IIT Mandi. So my name is Ajay Soni, and I'm from School of Physical Sciences. Earlier, it used to be like a School of Basic Sciences. Now we have a School of Physical Sciences at IIT Mandi. And let me just give you the idea when I'm sitting. So the IIT Mandi is in the foothills of the Himalaya. Somewhere here, and this is Delhi, and this is Jaipur, and Indore is somewhere here. So this is a relatively new IIT, so it's more than like 12 to 13 years old, and we have like a blend of the degree programs from UG to PG to PhD, and we have like a good nice setup for the academic environment, as well as the facilities like AMRC, C4D, FED, and BioX centers. So these are the facilities, and this is the bird eye view of the two campuses. What we have is what you see on the left hand side is the North Campus, where we have mostly the UG academic activity, and right inside is the South Campus, where we have like mostly the major research facility has been housed, and the PG programs are running in the, especially the science PG programs are running in the South Campus. All right, so this is the research activity in my group. We work on the basic theme of charge transport in the thermoelectric materials. We also work on the optoelectronic materials. We also work on the graphene and graphene-based functional devices. So there are a few materials which are relevant to the present talk, like bismuth telluride, some argyrite samples, some minerals, and some of the cubic tin telluride-based materials. We also do a lot of instrumentation for the customized measurement, so that we can measure the physical properties on demand, what we want actually. Okay, and we work on like ultra thin layered materials at the atomically thin layer, and try to understand the photoresponse of these materials. And we work on these graphene based materials to make some devices which are metal free and all carbon based devices. And you can have like the patterning of the materials for the conductive ink, and there are several publication you can see came out from the research. And our research is majorly funded by the various funding agencies, and we are thankful to them. So let me just give you the overview that it is last year was the 200th year of the Seaback effect, which is the basic fundamental effect of the thermoelectric research. I'll come to the what is thermoelectric research is. Okay, and this particular effect is known for 200 years, but the application of this effect into the energy requirement is very recent. You can say like nearly around 60 years or something, and since then the research is evolving. And this is the textbook definition of the Seaback effect, where you have a material A and a material B. When you have when you join them together, you have two junctions, and if you keep the two junctions of the two wires at two different temperatures, so you create a thermal gradient between the two materials, and this thermal gradient actually changed the chemical potential at the two junction of the two materials, and that gives rise to, and the change in the difference of the chemical potential actually is the voltage which is generated because of the thermal gradient. And that voltage which is generated, you can use it for the low power electronic devices. So this is the fundamental theme of the thermoelectricity research. So what you are doing is you are utilizing thermal gradient in the environment, or the waste heat, or the heat in the surrounding, and converting that heat into the electricity, useful electricity. And that's how actually you are generating the energy resources. So this is the outline of the talk, where I will be talking about what are the energy resources, what is the demand and supply, because this faculty development program has the basic theme where you are talking about the renewable resources of the energy. I'll give you the idea about what are the thermoelectric effects and the fundamental of the thermoelectric research, and how one can make the devices out of the materials, and what are the different architectures, and what are the state of the art materials which we are actually working in our lab. So if we look at the energy per capita energy consumption, okay, across the globe, what you see here is that it was like 600 kilowatt hour in 2005-6, which is like near around 16 to 17 years. And if you look at like in 10 years, 600 to it is like 1200, nearly 1200 or something. Okay, so it's like doubled in 10 years. So which means it is expected that the consumption will increase day by day, because the population is increasing, and we have like multiple industries coming up, and so the demand will increase continuously. Okay, and if you look at the resources what we have at this moment, so I mean like these are the non-renewable resources, where I mean like they are because of the consumption, they are slowly we are actually having a less resources for that. For example, we rely majorly on the coal, okay, and the other natural resources, and slowly these resources are vanishing, and because of the consumption. And if we look at the total energy consumption in 2005 to 2050, 2040, you look at like it's increasing, and you are going to have like more resources. So you need to find out the the alternative of the resources. And you know that if you talk about the energy resources what we have. One is the sun, which is continuously giving us the sunlight, and we are using solar cells and photovoltaic to convert the solar energy into the electrical energy. And then we have like multiple resources, like you can have the motion or the mechanical energy, which can be converted into the electrical energy using the piezoelectric effect. You can have like the photovoltaics, where the light is converted into the electrical energy, and then you have the electromagnetic radiation, where you can, using the induction, you can convert into the useful electricity. Of course, you have the chemical energy, where the energy or the battery storage is one of the resources where you can utilize the resources for the electrical energy. One of the resource what we have is the temperature gradient, because heat is omnipresent across the globe, and you can tap in that. And if you look at the research in particularly the area of thermoelectricity is increasing day by day. If you look at like from 1960s to 1990s, there were very few people were working in this area, and now after 1990s or something, once the nanotechnology has come up into the boom, you have like rise in the publication in this area, and a lot of researchers are working in that area. And you know that the heat is omnipresent, whether you talk about the industry, whether you talk about the automobiles, whether you talk about the home appliances which you use, like the Tillu pump at home for taking the water from ground to the top of the house on the roof. And of course, we also are the source of energy. If you consider that 37 degrees centigrade is the body temperature, and if you are in the cold place like Himachal or somewhere, you have like 5 degree or something. Okay, so you have a thermal gradient from 35 to 5, which is like 30 degree centigrade. So that also is a source of heat in one sense. And if you look at like the electricity which is produced in the power plants or the hydroelectric plant, there you have the heat is generated because of the mechanical motion. And if you transport that energy to the houses or for the domestic purpose, even there also, because of the Joule heating, the high current is passed through the wires, you have the heat generated, and then it is lost in the form of the heat. So means whatsoever the energy you are producing, 66%, nearly 66%, it is lost in the form of the waste heat. Only we are utilizing the 34%. So I mean, like there are various resources from where we can generate the electricity, or where you have the heat which is present, omnipresent there. Now, the thermoelectricity is a phenomena which works on the principle that you can convert the thermal energy or the heat into the electricity, and vice versa. So you can also, like if you have the electrical energy, you can create the high temperature and low temperature. So and that you can utilize it for creating the eco-friendly refrigeration that we will talk in next few slides. So if you can utilize this 66% energy and convert into the electrical energy, actually you are creating the resources for that. Okay, so thermoelectricity has three fundamental effects. I mean, like this particular research has like based on the three fundamental effects. We call them as like a Seaback effect, Peltier effect, and the Thomson effect. So in Seaback effect, what you have is you keep the material in a temperature gradient, and then because of the change in the chemical potential, you have the voltage generator, and you can utilize that voltage. So this particular research, we call it as the power generation, which is based on the Seaback effect. Second one is the Peltier effect, where you pass the current through the wires, and what it does, it creates in the cold at one junction it creates the refrigeration, another junction it creates the heat actually. Okay, so now by passing the current into the thermoelectric module, you can create environmental friendly refrigeration as well. So here you need like two different kind of material in one. I mean, like you can say that the N-type semiconductor and P-type semiconductor, and you can have the same effect like Seaback effect in the single material just because at the two different temperatures you have the different chemical potential of that material, and that can generate the electricity as well. Okay, and that effect you call it as a Thomson effect. So as I mentioned that the Seaback effect, what you can, I mean, like how do you utilize that? So you have a P-type semiconductor and an N-type semiconductor. So I don't need to tell you about what is the P-type and N-type, because this is like a textbook keyword. P-type semiconductors means it is dominated by the P-type charge carriers. We call them as a holes. And N-type semiconductors means it has like the electrons as the majority charge carriers. And if you keep them under the thermal gradient, like you keep them into the hot junction and the cold junction, it generates the power. And so this particular module, we call it as a single leg device. Okay, and the Peltier effect, where you have like you connect to the power and you have the heat absorbed at certain places, you call them as a refrigeration. But these are single leg devices, so the efficiency is poor. So what you need to do is you need to create a multi-segment device, um, which can have like the addition of the voltage generated through those devices. Okay. And there are different ways of making these kind of devices. So what you can do is, this is called the simple single leg device, kept between the cold and hot side, and you can take out the voltage generated across these materials, and you can use them. There is other way actually is that, but here it works between the two temperature only, two temperature range only, mean like, okay, two different temperatures. Here what the another device module you can create is like the segmented devices, where you can have like different kind of materials, n-type materials and different kind of p-type materials, to segment them one after the other, and then you can utilize even to the larger temperature range. And then third one actually is like, you call them as a cascade devices, where you have like N, P, P, N junction, and then you put them into the another P, N junction. So, and this works in a typical temperature range, and this works in a typical temperature range. So actually, you can enhance the utility of the devices. Now, if you talk about these thermoelectric devices, and when you talk about the conversion of any kind of energy, you always talk about the efficiency, because that's the important parameter which defines whether the materials or the technology can go up to the commercial level or not. Okay. So these thermoelectric modules, they also have like the thermoelectric efficiency, which is like a Carnot efficiency. You define it. So it has like the hot temperature minus cold temperature normalized over the hot temperature. So which means this depends on the temperature gradient. And there is another parameter, we call it as a ZT or the ZT. We call it as a thermoelectric figure of merit. I'll talk about this parameter in later slides. So you have 1 plus ZT under the square root minus 1 divided by square root of 1 plus ZT plus TC by TH. So this particular parameter, it depends on the material, because ZT depends on the materials parameter, while TH minus TH, which is mostly the engineering aspect of this efficiency. So when you talk about the conversion efficiency, you have to consider both the aspect, the material aspect as well as the engineering aspect. And of course, if you wanted to improve the efficiency, you need to have like multiple segment devices. Okay, so now we'll talk about the efficiency of the thermoelectric materials. Right now, the efficiency, you can think about it, is 5 to 8%. So it is very difficult to compete with the commercially available resources. But certainly, if we have a material which has like much better figure of merit, then we could compete even with the commercially available refrigeration technology or the power generation technology as well. And you know that you might have a talk on the solar cells as well, or the photovoltaics. I have seen the program yesterday. I mean, like there was a talk yesterday. So where the efficiency is almost like 20% or something, okay, for the solar cells, and now it has gone like up to 40% or something. So, but keep that in mind. This efficiency is poor, but it is tapping the heat or the thermal gradient which are omnipresent in the atmosphere, and we do not have a scope to utilize them, and they contribute to the global warming. So which means if we are able to tap them, that means we are contributing not only to the tapping, I mean, like not only working on the global warming, but we are actually creating some of the resources. Even the 20% of the heat, I mean, like the waste heat, if we can utilize that, also becomes a good resource of the electricity. All right. So I mean, like this efficiency is a function of like different kind of temperatures. And if you talk about like 50 degrees centigrade in summers, indoor might reach around like 42 degrees centigrade or something. Okay. And if you have like the cold water or the ice somewhere, you can in fact generate the electricity just keeping the module outside as well as connected to the cold water. And you can have like the charger for your phone, or maybe the devices what you have it. Yeah. All right. So, what are the capabilities and the possibilities with the thermoelectric module? So, let us talk about the body heat, as I was talking about one of the slide. So, the thermal energy which is released from the human body is 6 milliwatt per centimeter square. Keep that these numbers in mind. And if you make a device which has a conversion efficiency uh, with 5 Kelvin temperature gradient, which is like 0.3 percent. Okay, so this is the poorest I can imagine about any of the module. Okay, so which means you are generating a power which is like 20 microwatt per centimeter square. And if you look at the requirement for a watch, okay, which is like 40 microwatt or something. Okay, like this is Citizen has a watch which requires like 14 microwatt or something. Okay, so even if you are creating a very poor power sources that can actually power up the watch which you are wearing actually. And this is made up of the 2000 pairs of the bismetal, right? Okay, and you know that these days we are wearing a lot of the wearable devices, starting from the headbands to the earpods, and then we have the wristwatches, the medical devices. Okay, and you know that if you walk, you have a different parts of the body where. Excuse me. Excuse me. Any question? All right.
No, no, sir.
Okay, so I mean, like you can have like these devices where you can tap in the body heat and power up these devices, because these devices are actually at the low power devices. So I mean, like you can create like a lot of, so these are the watches where you have the thermoelectric generators, and this can power up like you know that last 2-3 years we have been struggling with the pandemic situation, and every day you are checking your oxygen level, or the thermometer, you are checking your temperature or something. Okay, then you are using the battery for that. But what you can do is, or maybe if there is a patient, you can just put the thermoelectric generator and connect it to your oximeter or the temperature meter. You get the continuous value, and here you don't need to power up this one because they are using the body temperature. And in fact, if you are having a fever or something, you have a much better power generated out of the thermoelectric module. Okay, I'm not saying that you need to have a fever for that, but even the normal temperature is sufficient. Yeah. So one can actually create a lot of these kind of devices, and I mean, like some of the devices are already in market and people are using it. But yeah, this technology is so powerful and strong that you can create it. Okay, and I mean, like one of the things which we also have done it in our lab actually, to utilize when you are heating when you are boiling the water or something, you can utilize that heat as well. Okay, and you can power up your what do you call, like the mobile or the devices. In fact, in our lab we were able to create um, uh, a power source which can actually run the small DC motor. So which means it's a good amount of the power which is generated. Okay, so by using putting these devices on the cooking appliances or something, you will be able to create some of the power. Okay, of course for cooking the food you need to have like some of the heat or fire to, or the high temperature, and you can utilize even that for getting the so you can see here that this is the pan which is connected to thermoelectric module, so you have the light there. And the most successful story for this thermoelectric research is in the space application, where the human race, actually we are looking for somebody outside the solar system, whether we have somebody to talk or something. Okay, and there are a lot of space mission where uh, the satellite have been launched and sent to the outer space there to power up the electronics for sending the information or for the communications. You need to have a power source. Okay, one of the sources the solar energy, but you know that in outer space, if you are right behind some of the planet or something, you do not have the solar cell, and then you will not be able to communicate. So in that case, these kind of devices are you can place them at the remote location and they can power up the electronics continuously. For example, Voyager 1 and Voyager 2 and the Sputnik, where they use this silicon germanium based radio thermoelectric generator, which you might have heard in movie called Mission Mangal as well, that so it uses like the like the radio isotope where you create the extremely high energy or the heat and connect them to the thermoelectric generator, and the outside temperature for the solar system is around 2 Kelvin or something. So you have enough thermal gradient where you can convert that thermal gradient into the electricity. So this is one of the most successful story of the thermoelectric research, where in fact the Voyager, which has moved out of the solar system, also had the radio isotope thermoelectric generator, which power up the remote devices for that. Yeah. And this is one of the scheme of the device. Okay, you have like the nuclear fission inside here, which creates like extremely high energy, and then you have these thermoelectric modules right outside, and then you have the outside temperature. So this is like cold region, this is the hot region, and in between these you keep these thermoelectric devices and get the power out of it. So radioactive decay is this the fuel for the heat, and the heat flows through the thermocouple or the like the thermoelectric devices, which can generate the electricity, and you can run them. So the limitation comes from the half-life of the radioactive fuel. Actually, okay, it's not from the thermoelectric module, and you can see like there are various materials like lead telluride, lead tin telluride, silicon germanium, lead telluride, and some of the tags material which have been used for the navigation satellite or the meteorological satellite, Mars landers, Jupiter asteroid belt, or there are many missions which has been planned, and where and you can see this is one of the device which has worked on already for 22 years, or still operating over the 38 years or something. Okay, so you can use them for several years and without okay. So most of the materials which have been used in making these thermoelectric materials, the thermoelectric devices, are the germanium, tellurium, and AgSbT2. So these are the silver, antimony, and tellurium based materials for the p-type thermoelectric materials, which they work in the range of like 200 to 500 degrees centigrade. Bismuth telluride based modules, they work at the room temperature or below for creating the environmental friendly refrigeration technology. There are hybrid modules of the bismuth telluride and antimony telluride, lead telluride, which works at like 300 degrees, 60 degrees centigrade or above room temperature. There are lead telluride based materials which works up to the 600 degrees centigrade or something. Okay. Just excuse me, just hold on for a while. Hello. Hello. Sorry, phone call from my colleague. Yeah. All right. So we were talking about the material system, the materials aspect of the thermoelectric module, and you can see there are few materials which are called the champion materials, like germanium telluride, bismuth telluride, lead telluride, and some of the oxide-based materials. And these materials, silicon germanium-based materials, which works in the different temperature range. So the space application, mostly the materials which have been used are the silicon germanium based materials, and for room temperature it is the bismuth telluride based material have been utilized actually. Yeah. So which means the material aspects are very important. Okay, and let me just give you one overview that what are the other device architecture you can think about it. If you can have a curvature light which can be fixed on the exhaust of the car or the two-wheelers or the automobile industry, where you have the major exhaust pipe where you have the major heat generated, and you can utilize that to power up even the LED lights on the backlight, okay, or the camera which is put on the backside, or maybe some of the chargers which you are keeping inside. Okay, even so, which means this heat which was ultimately going to the environment, you are tapping that heat actually to convert, okay, into the like you are utilizing to power, okay. That will increase the efficiency of the car engine as well, because you are not putting the load of the powering of the electronic devices on the car engine. Yeah. You can also have like the flexible devices which can take the shape of the body part or this thing, and then you can have like different kind of resources for, like you can create a battery out of it for the devices. Yeah. So as I talked about the figure of merit, I'm almost in the half of my talk. So I gave you the overview that how the industries can tap in this particular technology. Now I'll talk about the material aspect and how you work in the lab and create those kind of materials which can be translated into the technology. So as I mentioned that the efficiency depends on one of the parameter which depends on the materials parameter. It's called thermoelectric figure of merit, and this is defined by the mathematical formulation ZT is equals to S square sigma multiplied by T divided by K. So if you understand this equation, half of my job is done. This S is the thermoelectric power of the material, okay, which is the Seaback coefficient what you get for the material. The sigma is the electrical conductivity of the material. K is the thermal conductivity of the material, and T is the temperature, okay, where this material can be functional or it is the operating temperature. So this depends on the materials parameter. This is electrical conductivity. So what you want, a material which is good, which has a good electrical conductivity, and a material which has a very poor thermal conductivity. So you need a material which doesn't conduct the heat. So it is insulating for the heat, but it conducts the electricity. So which is like it is good conductor for the electricity, okay. And if you look at these parameters, S is the thermoelectric power. This is again a mathematical formulation, so it depends on the effective mass of the charge carriers, and it depends on the number of charge carriers. Rest of these parameters are actually the constant, okay. So which means there are two different parameters here: effective mass of the charge carriers, electrons and holes, and number of charge carriers. Now, if we look at the electrical conductivity, it depends on the number of charge carriers and the mobility of the charge carriers. And this is the electronic charge, which is again a constant. So now, and the thermal conductivity has two different parts. One part is depends on the lattice part, and the another part which depends on the charge carriers or the electrical part actually. Okay, so which means you can see if you have more number of charge carriers, your thermal power will be low, while your electrical conductivity will be high. Now, if you have more number of charge carriers, this electronic part of the thermal conductivity will be high. So which means more number of charge carriers are not good for optimization of this particular equation. So you need a material which can have a much better optimization of the charge carriers. So in that context, you can think about it. Okay, if you look at the number of charge carriers in the material, so if you go like 10 to the power 22, which is the metallic region, which means the metals like silver, copper, gold, nickel, iron, these are the materials which has large number of charge carriers. They have a good electrical conductivity, but because number of charge carriers are large, the poor thermoelectric power. So which means thermoelectric power is poor. So which means metals are not good for the thermoelectric research. Now you consider the other end of the charge carriers where the insulators are there, or you say it is the plastic materials or the insulators or non-conducting material, where you have a electrical conductivity which is poor, okay, and you have the Seaback coefficient which is large, okay, and you also have like the thermal conductivity is poor, so which means you cannot have insulators also as a good thermoelectric material. So you need a material which has the optimized value of the charge carriers, and these kind of materials are actually the narrow bandgap semiconductors, which are good for the thermoelectric research where the charge carriers are optimized. Okay, so this interdependency of these three parameters, Seaback coefficient, electrical conductivity, and thermoelectricity, thermal conductivity is a roadblock for these materials in the material aspect. Okay, but what you want actually, you need to have a material which can have a very high thermoelectric figure of merit. So what you need to do is you need to enhance the power factor, which is the numerator of the equation, and you have to lower the thermal conductivity. So you need a material which has higher the electrical contribution, while it has like the poor thermal conduction. Okay, so there are various ways of doing that, okay, in science. Okay, so you can optimize the charge carriers. You can do the band engineering where you can have like multiple bands, the electronic bands in the valence band. You can bring the contribution from multiple valence band together, and then you can have the enhanced power factor. So you know that when you talk about band engineering, you talk about the effective mass actually. So you are working on the effective mass and you are working on the charge carriers as well. Okay. While if you look at like in this equation, this 1, 2, and 3 parameters depend on the number of charge carriers or the electrons. Okay, they are interdependent, but this is an independent parameter. Okay, so which is called the latest part of the thermal conductivity, which depends on the elastic property of the solids, which depends on the atomic vibrations, or we call them as the phonons, which contributes to the thermal conductivity of the solids. Okay. So what you can do is you can enhance either this one, or you can reduce this one, or you can bring this one to the as minimum as possible. And how you can do is that you can create crystal defects, point defect dislocations, precipitates, or phonon red bloods, or there are like multiple scattering centers you can create by nanostructuring, or you choose the material which has like a structural complexity or the superionic semiconductors, so that you independently reduce the scale, because controlling these two will require control of this one also. So which means if you can minimize this one, you can actually have the optimization of that. Okay. So there are several challenges for this particular research. So what you need to do is you need to decouple the heat and charge flow. Okay, and you need to have a right kind of thing. So in our lab, we work on the fundamental science of these materials to understand. So when you talk about the only the latest part of the thermal conductivity, it depends on the heat capacity of the material. It depends on the overall group velocity of the phonons in the material, and it depends on the mean free path of the phonons. So, okay. So when you talk about, when you create a nanostructures, you are creating a lot of defects like the interfaces and the grain boundaries in the materials that can become the phonon scattering centers, which can reduce the thermal conductivity. Okay, so this we have done it in this telluride-based materials, where we grew these materials in nanoform and then make a composite out of it, and we could achieve like a good thermoelectric figure of merit by controlling the mean free path of the solids. We also work on some of the materials like SNT based material, and where we found that you can reduce the latest part of the thermal conductivity by creating some defects. Okay, so we actually broke some of the invergent symmetry of these materials. These are the cubing materials, and we actually disturbed the overall group velocity of the phonons. And now we are working on some of the materials which has like the heat cap, I mean like the poor heat capacity, the like large unit cell materials where you have like poor heat capacity and there you can tap in. So we actually control all these three parameters to get the poor thermal conductivity in these materials, and these are some of the publications from our group and the collaborators which came up in this particular research. So what you need to do is you need to, if you wanted to create a efficient thermoelectric materials, you need to understand the microscopic process which are controlling the thermal conductivity, and if you can tap in, then perhaps you have the advantage over there. So I will just take a few examples in the materials aspect. So you can see this is the temperature range of the thermoelectric materials, and this is the figure of merit. So what you can see is that the bismuth antimony telluride or bismuth telluride based materials, they work in the low temperature like room temperature applications. There are materials like lead telluride based material, they work in the mid temperature range, and there are silicon germanium which works in the high temperature range. And you can see the the efficiency, or I mean like the thermoelectric figure of merit is around 1.5 or something. Recently we have achieved the figure of merit which is 2.4, which goes actually beyond this particular figure. And if you look at the evolution of the research from last 20 years or something, you can see like there are a lot of materials. The red color represents the n-type p-type material, and the red color green color represents the n-type material. So the combination of n-type and p-type materials. So, and this is the temperature range. So you can see the people have reported some of the figure of merit which is nearly around 2.4 or 2.5. Okay, so in our group we work on so I'll take another 5 minutes to complete my talk. I will just discuss about the material aspect of the research what we are doing in the lab. So SNT is a material which is the homologue of PBT, which is the champion material, which is already in the commercial application, or which is already there. But the problem is that it has lead. Now lead is it's not environmental friendly, so it's a toxic material. So if you wanted to work with the environmental friendly technology, then why do you wanted to work with the materials which are toxic or something? Okay, so the alternative actually is you choose the homologue of the PBT, which has the same crystal structure like FCC cubic, okay, which has the similar lattice constant, which has the same space group, but the difference here is the band gap. Okay, so you have like SNT has a smaller band gap. Okay, the number of charge carriers are higher. The figure of, I mean, like if you talk about the Seaback coefficient, it is small because you have large number of charge carriers here, and ZT is almost half. Okay, but if you can tap in some of the signs of the the control of the valence band, two valence band which exist in both of these materials, so you can see here that the band gap here for the BBT is large, while the gap between the two heavy and light valence band is small. While in SNT you have a band gap which is the bottom of the conduction band to top of the valence band is small, while the gap between the light valence band and the heavy valence band, it is large here. Okay, so if you can tap in these two multiple valence band together, then you can perhaps have the large effective mass. So what I'm saying here is that you can compare. Suppose a person has to walk from his home to the office alone, that means he can run with his own speed actually. Okay, but if I ask somebody that you have to bring your friend also together, so that means the person has to wait for the friend to be ready, then he has to match the speed of the friend and then come actually. So which will slow down the speed or the mobility of that particular person. Okay, so what we are doing actually, that we are trying to bring the contribution of the two valence band, that will actually the slow down, and that will increase the because we are increasing the effective mass of the charge carrier, so that will increase the Seaback coefficient. Okay, so this is the data which we have seen it. Okay, for the MN doped tin SN telluride. So this MN doping actually plays a significant role, which doping actually changes the Fermi energy in these materials, which can be reflected from the number of charge carriers as well as the mobility. And you can see that this is the Pisarenko plot as a function of the charge carriers for the Seaback coefficient. This is the line which shows that these are below this line, the materials are not good. So the materials what we have prepared actually have a better performance as well. Okay. But the interesting aspect here is the lattice thermal conductivity. So if you look at here, this is the usual pattern for the lattice thermal conductivity of the solids. You have a peak which represents the scattering of like the interaction of the electron phonons. Okay, and this is the peak which shows that this is the crystalline, perfectly crystalline solid. But if you do not have this peak, actually, if you ended up in getting this kind of behavior, that means it shows that it's a glassy behavior in the material. Okay, so you can see that for the pure SNT as well as the mild doping of the SNT, you have this the behavior which is for the normal solid. But if you increase the doping, you actually gets into the glassy behavior, and we try to understand what is this exactly it is happening. So if you understand that, okay, this is the SNT, so this tin sits and it's create a very actually creates the like new modes which have been seen in the Raman spectroscopy of these materials. So you can see this the MN doping. So this is pure, and there is a slight jump in the two modes. These two modes represent the phonon modes or the atomic vibrations, or they actually represent the chemical environment across, around the tellurium. So if the chemical environment around the tellurium changes, you have a shift in these modes, which is visible here. But the interesting part here is at the low frequency range, where you can see that there are, this is the pure compound and this is the doped compound. So you have like new modes which are coming up, and these new modes are coming up because of the change in the inversion symmetry, the enharmonicity which is created, and that's actually create the phonon scattering center, and that can reduce the lattice thermal conductivity in this material. So you actually are targeting the phonon group velocity in this material, and this is generic actually. This is the sample we got it from our collaborator Dr. Kanishka Biswas and Professor Wagmara in JNCSAR. And these modes are actually available. I mean, like they come if you dope it with anything actually, okay, in SNT, like germanium, Mn, or anything actually you dope it. So which means this depends on the doping level what you have it, and that actually create a poor thermal conductivity in these materials. And these materials have like very high figure of merit. It was reported in the energy environmental science. We also worked on some other materials like the AGSBT2 with Professor Biswas and Professor Wagmare, the recent work which was published in Science last year, where what I mean, like these are the chemists, so they create like the samples as per the demand, actually as per the desired. Okay, so here the interesting aspect is that when you dope something, you create a disorder. But when you dope or when you put something, if it increase the orderness in the material, that's the exciting science actually. Okay, so with this particular material, with the CD doping, 6% CD doping or something, which in AGSBT2 gives rise to the more ordering in these materials, which actually gives the good electrical transport in the material, and poor thermal conductivity because you are putting the cadmium into it, okay, which can create the phonon scattering center. And now you can see the ZT for that particular research is almost like 2.5 or something. Okay, so this is extremely high, and the science is very interesting, so that's what it is published in Science. And now another aspect of so this is the final example for my talk. I'll talk about like the bismuth telluride is another champion material, and there are a lot of research have been going on in last 10 years or something. Okay, from like 1950s to 2000 or something, the figure of merit for the bismuth telluride based materials was around like 0.5, or it has reached around 1 in almost like 2008 or something. Okay, where this was published in Science by one of the Boston and MIT group. So you have a bulk material which has the efficiency like this one, and you what you do is you break them, okay, and then you make a composite out of it again, okay, and you have the nanocrystals, okay, so the efficiency increases. So figure of merit has increased, and it has gone up to 1.4 or 1.5. Now it has gone like 1.8 or 2 in these kind of materials. So the idea was actually to create more phonon scattering centers, or create some of the interfaces, or so what they do is these interfaces, the low energy electrons, they will not transport the heat, okay, or the electricity, but the high energy electrons will do that. Okay, and that way actually you can control some of the charge carriers in these materials, in these narrow band gap materials, and then one can design different kind of strategies in the nano composite. So this is one of the things which we also have done it in like 10 years ago or something. Okay, and we could utilize the interfaces for the what do you call it, like to get the more scattering centers. Okay, and so what we do actually is one can create an anharmonicity in the materials which can affect the phonon thermal conductivity by the elastic properties, which depends on the Grunissen parameter of the materials. So by creating different kind of defects, you can create the materials. Okay, and recently we worked on the bismuth telluride and germanium doped bismuth telluride based materials, where when you make these materials, they have a different kind of structures which are interesting for the thermoelectric research. And these materials are also like the best quantum materials, like to study the topological insulating properties. Okay, so this you can see from the bend structure here. So if you have like the surface calculation shows that there is a Dirac cone, and these materials, because of their structure, okay, the layered nature, these materials have a high anharmonicity, very high Grunissen parameter, and that can lead to the very poor phonon thermal conductivity in these materials. And these materials are very exciting to work on the thermoelectric research. All right, and some of the aspect of the complex structures we also work. I'm not going to go into the details here, and with that I would like to acknowledge the funding agencies who have supported our research. This is my group, majorly the students who work in the lab, and I just present the work which has been done by them, and the collaborators which helps us in several aspects of the research, I mean, like learning the new things. Okay, and there are a few students who have been passed out from our group. They are doing postdoc in outside India in various universities. And with that, I would like to thank all of you for patiently listening to me. And if you have any questions, I will be happy to answer.
Thank you. Thank you very much, sir. Now the session is open for the question answer. If any participant has any question, kindly put your question in chat box, or you can raise your hand. I will make you your mic unmute so that you can ask your question. Any participant? Maybe say they will take some time. Meanwhile, I have 2 or 3 queries.
Yep.
From my side.
Yeah,
like in one of your slides, you mentioned that the Seaback effect is somehow correlated with the conductivity, concentration of the charge carriers and mobility, mu.
Yep.
My question is, if N is increasing, it means it should directly reflect the conductivity of any medium.
Yes.
And in our case, N increasing, it's somehow decreasing the ZT effect, or you can say the S effect is decreasing. Like S is, I think, Seaback coefficient.
Yes.
So the conductivity must be high, because ZT shares the conductivity should be directly proportional to the conductivity.
Yes. So what happens is, when you talk about the number of charge carriers, the limitations come from the Weidmann-Franz law.
Okay.
Because Weidmann-Franz law will increase the electronic part of the thermal conductivity, and that will increase your denominator. So that's one of the biggest hurdle. Second part is, if you look at the Seaback coefficient is inversely proportional to the number of charge carriers. So if you have like more number of charge carriers, the Seaback coefficient is low. But if you can tap in, even with the number of charge carriers high, which is the case in the SNTE, but what we are targeting here is to increase the effective mass. So even if the number of charge carriers are large, you ask them to walk slow. Okay.
Right.
Okay, so which means the mobility is poor now, actually. Okay, so
yeah. Okay, and secondary is like mobility and the phonon, because in one of the area, because we know that if it's a material solid, we increase the temperature, phonon vibration will increase, and this is somehow decreasing our mobility.
Yes.
And as far as like thermal conductivity, we need a good mobility, I think.
No, if you are talking about the electronic part, you need the mobility. But okay, but because we wanted to isolate this the electronic part in the thermal conductivity.
So we are discussing about ionic conductivity or something.
So when you talk about the ionic conductivity, which means the superionic conductors, okay.
Right.
Okay, so there actually what happens is the superionic conductors, they behave like a liquid. So which means the phonons are completely different here.
Okay, right.
Okay,
right.
the phonons are completely different. So what happens is, when you talk about the superionic conductors, so you can have like 2 atoms, they can like go up to the half of the distance of the next nearest atom. Okay, so now you do not know actually at the middle of this one what kind of atom it's sitting. So that's what's like a liquid like behavior. But still, because these are ionic ions, so they can conduct the electricity, but they disturb the phonons extremely high.
Right.
Yeah. So this is the case for the copper telluride and copper selenide.
Right. And the last is in one of the slide in like the paper by MIT, I think they published in Nature. They are showing that they are increasing the orderness of the sample.
Okay, so that's the
and
science
simultaneously, in one of the slides we are showing that the demerits. If we want to remove the demerits of K of L, we should make the material point defect or some deformations are required. So they are contradictory, I think. Yes. In one part.
So are you talking about this paper actually? Yes, this is
science.
Yeah. Okay. So this is very, very interesting science. The reason being, when you dope, the general understanding is that it will create the disorder.
Right.
It will disturb the structure. Okay. But it is the case here, this cadmium has the ionic size, which is exactly in middle of the silver and antimony.
Okay.
Okay. So now when you are putting it, it is creating more orderliness.
Right.
Okay. So this is very interesting aspect of this particular research. Okay. So the interesting science is because the size is exactly in the middle. So it is creating ordering. But since it is the Z contrast is there, at the same time, it is creating the disorder which is seen in the low temperature transport as well. Yeah. And some of the localized states which contribute to the charge transfer. So it's a very interesting science in this kind of material.
Yeah, that's why this was so surprising also, because the same thing we are we are performing some other way and it's performing some other way.
Yes.
Very nice.
Yes.
So interesting work, sir. Very interesting work.
Yeah.
Okay, I got one question from the Soumya. She's asking, can we complement solar energy with thermoelectricity to augment both their drawbacks?
Okay. So the answer is yes. Okay. And you can have a solar thermoelectric generator. So in the sense, like when you have like solar concentrator, you concentrate the whole solar light into one place on your solar cell. Okay. So now it heats up. All right. So and you can, what you can do is you can keep the solar cell on top. It absorbs the light. At the same time, it heats up the solar cell. Now you put the thermoelectric generator right underneath it. Okay. So now it will utilize the heat which is here at the solar cell and convert that into. So you can have even better efficiency from the solar thermoelectric generator. Very good question, Soumya. Yeah.
Any more questions from participant sides? You can post your question in chat box, or you can raise your hand so that I can make your mic unmute. You can ask a question directly to sir. Anyone? I think it's all about today, and really so interesting, so informative talk, sir. Because we are working on solar cells and rechargeable batteries, and this is really a new pathway for me to think about these type of materials as well.
Yes. Yes. Yeah. Thank you.
Uttam Sharma, sir. Are you there, sir? Okay, so I request our HOD, Dr. Uttam Sharma, sir, to put their vote of thanks to Ajay Soni, sir.
On behalf of Sri Vaishno Vidyapit Vishwavidyalaya and Department of Physics, I would like to thank our today's resource person, Dr. Ajay Soni, for sparing his valuable time and giving valuable insights about his research work. And the theme of this FDP is very recent and related to nearby future requirement of the energy. So I would like to congratulate to Dr. Amit Saxena, Dr. Neetu Kataria and Dr. Pragya Palod also for taking up this challenge to conduct FDP on a issue like renewable energy. So I would like to thank once again Dr. Ajay Soni, and hope we'll meet in a physical mode to our university so that our students and other faculty can get more benefits from your research and development work. Thank you.
Yeah, I would like to be okay. So if any student has a question, they can drop an email to me as well. Yeah.
Okay,
there
sir.
is mail ID also.
Yeah. So
we will share your mail ID with the participants, and it will be very good if you can share the presentation with us so that we can send it to the participants as well.
Okay, presentation is like maybe
anyway, we have the recording, so we'll try to take, and we will send the recording to you as well, sir.
Okay, yeah. Thank you very much.
Thank you, sir. And this is the announcement for all participants that for today's second shift, we'll conducting our session on Google Meet instead of Zoom. So all of you are requested to join through Google Meet. So thank you, Ajay sir. Once again,
okay.
Thank you.
Thank you very much. Thank you very much, all of you. Yeah, all the organizers. Thank you very much. Yeah.
Thank you, sir.
Thank you.